galaxies just looking as we would try to study the sky, for example, if we were down here on Earth looking through trees and clouds. You subtract out and ignore all of the galaxies and stars and see if there's some faint background that you can see. And in a really fantastic experiment, they did detect this hot fog, and this is a famous map that results from it. So what are you seeing here? So this is the whole universal sky, you know, where we're ignoring all the stars and galaxies. What do we see? This is a very exaggerated view of the intensity of this background that we call the microwave background. And these different colors represent differences in the intensity, and since everything that's hot radiates, this really is tantamount to giving different temperature differences of 1 part in 100,000 between this hot spot and this cold spot. So I haven't explained that well, but what you are seeing is a very exaggerated view of this background light that in fact shows extremely small differences in temperature. Now, if it weren't exaggerated like this to emphasize the differences in temperature, this is really what we saw. That is, the microwave background is absolutely uniform to 1 part in 100,000, meaning it's more uniform than the air in this room. And this is what the early universe started with. So there were these micro fluctuations in density and temperature that were absolutely minuscule. And so the question is, this is this hot fog that's expanding. How do we get galaxies out of it? Planets, stars. The micro fluctuations come, they're called quantum fluctuations, from the fact, like in the air in this room, which is pretty uniform, but not precisely because of the microscopic motion of the various atoms. So these quantum fluctuations, we believe, came from this burst of energy in which matter was created from it billions of a second after the Big Bang, and underwent an incredible expansion that produces homogeneity, but it wasn't perfect. It was inhomogeneous to 1 part in 100,000. So if you could really see here, there would be teeny ripples there. So the question is, can we take this situation now where we confirm that there is a hot fog back here, it's expanding, what caused this to happen such that billions of years later we see galaxies and stars? So scientists approach this in 2 ways. There are the people who are interested in theory who said, okay, let's take that situation, apply the laws of thermodynamics and gravity to it, and see what we get. And then those of us who were observers took the opposite, but supporting point of view. Let's actually use Hubble Space Telescope to look back in time to see exactly what the universe looks like when we look way out and can see back toward the Big Bang. Well, let me show you first the results that the theory people came up with, because they started this before we had Hubble Space Telescope. So, in fact, a number of groups took this inhomogeneity, 1 part in 100,000. Now, you can hardly see it, but basically, this is a very uniform glow here that starts off at thousands of degrees, and they put it in expansion just to see what gravity would do with these fluctuations, to see if the regions that were initially 1 part in 100,000 times more dense, if the increased gravity would cause them to condense and also attract the accretion of material onto them. And it's produced what I think is a fantastic result, and this is due to a graduate student, actually. I got this from just a couple of months ago, Doug Renahan. So what you're going to see here is a video that's 17 seconds long that starts at a time that's 50 million years after the Big Bang, which is actually a very small instant of time compared with how long ago the Big Bang was, to see what happens in this situation now if you take current laws as we understand them, okay? And you'll see this counter here going faster than you'll be able to read. Here is the predicted large-scale structure evolution of the universe in 17 seconds. And there it is. Come on, Bob. Happy Halloween. Bingo. So you'll see the micro fluctuations that you didn't even see because the homogeneity, in fact, they start to grow. And here was one of the biggest ones. Notice how its increased gravity continues to attract things to it. So you end up here, 14 billion years later, with what we call the cosmic web. That is, this initially hot, homogeneous material, those micro fluctuations did succeed in condensing and attracting more material so that you end up with much higher concentrations of mass and also big voids out here caused by the fact that all this material was accreted onto the more massive blobs. So that's the evolution of the universe. So the question is now, is that what it looks like? And I already showed you by mistake the answer. This is the result of a famous Sloan Digital Sky Survey, where for years, and they're still going, looking out in space to actually put where galaxies are. And this is what they see. They in fact see that there is this cosmic web of material now where you have voids. This is not a void here. This is the Earth in a way. So with their telescopes, you didn't access. In fact, since the plane of our galaxy, the Milky Way, has this obscuration, you do this survey actually above and below that plane. So the fact is, this is really large-scale structure of the current universe. And so it does look like, the fact is, this picture, starting with the Big Bang, largely homogeneous except for these micro fluctuations, will produce what we see. So we want more detail. So let's consider now the evolution of the universe in cosmology and try to determine exactly what does the future of the universe hold for us given the fact that it is now expanding. So here's the present time, okay, up at this point. We look out and we see galaxies. We project back into the past. There was a Big Bang. We know the universe is expanding. Since galaxies are influenced by their own gravity and there's an attractive force, there are two possibilities for the future of the universe. There could be sufficient material that the gravity of the galaxies arrests. It stops the expansion and the universe collapses back on itself. Or it may well be that there is insufficient material in the galaxies to stop the expansion and you would get it coasting indefinitely. So decades ago, these were the two cosmologies that were believed in, and the question was, is there any way we can undertake observations that will help us determine whether we live in what we think is a collapsing universe, in which the expansion will stop and will collapse again, or basically expand forever. So there were some of the really important early programs on Hubble telescope were devoted to trying to determine what the rate of expansion was and what the density of galaxies was, how strong this gravitational force was. And those teams determined the velocity of the expansion. And they did so by using supernovae, a certain type of supernova, which is an exploding star after it's used up all its hydrogen fuel, collapses and blows up. It turns out that we know from building models of their structure that they all tend to have the same brightness when they blow up. And therefore, they have a standard brightness or standard luminosity that enables us to determine exactly what their distance is simply from their relative brightnesses. So if you take an object of the same brightness and you put it at different distances, you know that the one that's further away is going to be fainter. And so these teams built up essentially a structure of the velocity of expansion of the universe with time. And what they concluded in very long ongoing programs was that the collapsing universe is not viable, that the expansion is great enough that the current density of galaxies cannot stop it. And so we live in an ever-expanding universe. But they came up with something that was even more interesting. And the fact is that not only is the universe expanding, as Hubble and Lemaitre found, its expansion is actually increasing in time. Now, we do not know of any force that would produce this. And so there is a source of energy in the universe right now whose origin we do not understand, and yet it is clear that it is counteracting the effects of gravity and producing an acceleration of the universe. This is a major discovery, and you know how major discoveries are rewarded. So the two teams that were involved in this received the Nobel Prize for their work that was largely done on Hubble. Perlmutter, Schmidt, and Reitz, whose office is just down the hall.